welcome to this class. Last time we looked at the adversarial learning principles for distribution estimation and sampling, correct. We will continue our discussions there, and today will be the conclusion or the final lecture on the adversarial learning part. The objective today is that I will talk about another paradigm which is called the Wasserstein's optimization or optimal transport, which, as I said in the previous class, this is a different paradigm in terms of how the distributional divergences are estimated. However, interestingly the final problem that we would be solving will again be a saddle point min-max optimization problem, as in the case of F divergence minimization, and that is why this is also called Wasserstein's GANs, generative adversarial network that way, but it is a whole new family of distributional divergence that it minimizes. So, we will look at that. I will also look at I will also talk about the other idea of what is known as GAN inversion, inverting the adversarial learning, and I will describe a couple of applications beyond sampling, okay, that can be solved using an adversarial optimization problem, and finally we will look at how to evaluate the quality of generative models. Okay, you have trained a generative model, you are getting some samples, how do you evaluate how good is the generation quality. Turns out that the optimal transport method that we will be looking at helps us in answering that question too, which is how do we evaluate a generative model. Those are the things that we will be looking at in this class. Okay. So, one observation that people made was that F divergence minimization, as we saw, is not stable for train. I mean, anybody who has some experience in training GANs would know that it is extremely hard to make these models converge. Why? Because by construction you are looking at a saddle point optimization problem, and the loss landscape can have multiple saddle points, and you do not know which saddle point is better than the other saddle point. Okay. In fact, any gradient based optimization in a very high number of parameter space is difficult to optimize, or rather it's hard to get into the global optima in such a situation. More so the case if you are looking for saddle points. Okay, here is an intuitive way of looking at it. I think I have mentioned that in the previous course also. I'll nevertheless mention it again. Typically, the optimizations that we will be solving while training neural networks will involve very large amount of parameters, right. I mean, today we have trillions of parameters. So, the space in which you are operating is a trillion parameter space or a billion parameter space and so on. Okay. Now, from optimization theory we know that if we have to designate a particular point on a function as an extremum point, we need the derivative to vanish, correct. And if that has to be a minima, there is the double derivative test that we look at, which says that if the double derivative is of one particular sign, then it is maxima, or the other particular sign it is minima, right. What is the equivalent of this idea in higher dimensions? In one dimension, if you have a single parameter, then of course you look at the sign of the double derivative, right. What happens in 2 dimensions? What is the equivalent in higher dimensions? Hessian matrices, right. But if you have to call a particular point as maxima or minima, you cannot look at Hessian matrix, but you will look at the signs of the eigenvalues of the Hessian matrix, right. And a particular point is going to be called as maxima if the Hessian matrix is positive, negative semi-definite, right, or is it the other way around? It is maxima if it is negative definite, not even negative semi-definite, it should be negative definite, and the other way around. Now, how do we know whether a particular matrix is positive definite or negative definite? One of the ways to do it is to study the sign of the eigenvalue of that matrix. If the sign of all the eigenvalues of that matrix are positive, then it is positive definite and vice versa. Now here is a simple thought experiment that we can think of. Let us say that I model the sign of the Hessian matrix, so the eigenvalue of the Hessian matrix as a Bernoulli random variable, which means that it has with a probability p the sign of the eigenvalue of the Hessian matrix can be positive, and with 1 minus p it is negative. Okay. Now for that matrix to be positive definite, so we want, if the order of matrix is n, then we want n trials, n independent trials of the Bernoulli random variable to turn out to be of one particular type, is not it? Now if we are looking at a billion parameter model, then the Hessian matrix is of order of billion squared, right, and we want so many Bernoulli trials to be turning out to be of the exact same outcome. Now even if you are, if the probability of the sign of the eigenvalue turning out to be positive or negative is very high, let us say it is 0.99, then multiplying 0.99 billion number of times will lead to a very small number, which means that in higher dimension, the more the number of dimensions are, the likelihood of hitting an extremum point, that is the global optima, is very low, right. So now what does that mean? That when we are training neural networks, how do we operate then? The only hope is that whatever minima that we hit, okay, or whatever extremum point that we hit is better than the other extremum point, is all that we can say. There is nothing called a global minima. That is why when training neural networks, people look at surrogate metrics. So let us say if you are looking at generative models, for instance, suppose we have some sort of a measure, a metric that would say how good is the quality of the generated data is. We will not track the loss landscape and try when and decide when to stop training. We will look at some other objective, some other surrogate metric of how good the model is, and we track that and stop the training looking at that, because it is not about loss getting minimized, because you cannot hit the global optima. It is whether the performance that you seek from the model has been reached. That's the way to look at it. Okay. Now if this is the case with well defined optimization problems, so here we are looking at a saddle point optimization problem, right. If you track the losses of the two neural networks that we have, which is the sampler network and the critique network, you will not see them decreasing, because that is not the objective. You know, for the t function, the objective is the maximization and the other way around, correct. You will not see that happening. So we will have to look at the surrogate metrics. Now this is one vague way of saying why this is stable, this is not stable. People have actually done a very systematic study to realize why the training of these kinds of paradigms, which involves the min-max optimization problem, is much more difficult. So to understand that, we will have to look at what is called as manifold hypothesis. Okay. So this is a hypothesis because there is no way that we can, so what is a hypothesis? Some conjuncture that cannot be, that does not have a proof yet, correct. So manifold hypothesis says that distributions of the real data that we get lie over a low dimensional manifold in the ambient space. What does this mean? So first of all we have to define what a manifold is. Think of manifold as a lower dimensional subspace of a vector space. It is not a subspace because it does not satisfy the properties of vector spaces. You can roughly think of it like a lower dimensional subspace in a vector space. I will not go to the definition of manifolds. It is basically a collection of vectors such that a few properties are satisfied. Okay. If I have to give an example of what a manifold is, let us say that I hold a thread here, I mean in my hand. Okay. It is not straight, the thread is not straight, but it has some curvy nature to it, but I have held a thread in my hand right now here. So all the points on that thread can be represented on a single one dimensional manifold in R3. Why R3? Because the space that we live in is R3, Now a thread in 3 dimensions can be looked into as a one dimensional manifold in R3. Do you see what I mean? Okay. Basically what I am saying is there exists a bijection between the points that are on the manifold, okay, and a low dimensional subspace is what I mean when I say that I have a manifold. Similarly, if I hold a paper with a thin paper with 0 thickness, I mean that does not exist in practice, but assume that something of that exists, then I am looking at a 2 dimensional manifold in R3 and so on. Okay. See, manifold hypothesis is a hypothesis that would say that the data that we get in practice, like images and text and all these kinds of data that we deal with, lie on a very low dimensional manifold in the ambient space. Okay. Why is that? I mean, I will just give you an intuitive explanation to this idea. Let us say that we again do this thought experiment where we take a 28 by 28 grid. Why 28 by 28? I am trying to generate the MNIST data set that has 28 by 28 dimensions. And what I do is the following: I toss a coin, and if my coin turns out to be head, I will fill one of the pixels in that grid using the white color. If the coin toss turns out to be black, then I will fill it with the black color. I am dealing with a binary image which can be white or black. Okay. How do I fill these 28 by 28 grids, which is 724 numbers? I will just toss a coin, and if it's head, I will fill it with one color. If it's tails, I will fill it with the other color. Okay. Now here is the question. So all the images generated via the above random experiments are in this particular space, right? Discrete 0, 1, 784. You have 784 dimensions, and all of them are binary dimensions. So this is the space that it lives in. Correct. So the question that I want to ask is, if I do this random experiment, what are the odds that I end up getting MNIST data set? So MNIST data set is again, I mean, it can be binarized. Let us say that MNIST data set only has white and black pixels. If I do this random experiment, what are the odds that I get MNIST data set? You can imagine it is very low, correct? Okay. Now why am I saying this? By the way, there is another nice way of putting this. I don't know if you know this. There is a problem called typewriter monkey problem, where the idea is you make a monkey sit in front of a typewriter. Do you know what a typewriter is? Gen Z people may not know what it is. Yeah, there used to be a machine, dedicated machine just to type things. We can't even imagine that those days exist. But yeah, so suppose you make a monkey sit in front of a typewriter and randomly press keys. The question is, what are the odds that it comes up with Shakespearean works? It is a non-zero probability, of course, but it is very low, correct. What is this saying? This is saying that the effective space that the data set like MNIST occupies in the ambient space is very tiny. In this whole space, okay, of binarized images of size 784, MNIST occupies a very tiny manifold is the idea. So this is called the manifold hypothesis. No matter what sort of data that you take, which occurs in practice, all the data that we get lies on a very low dimensional manifold compared to the ambient space that it lies in. So that is the idea. You can imagine, right? I mean, think of all the color images of a particular size. Let us take for example this celeb A data set, right, that contains the pictures of human faces. Now how much space does it occupy in the ambient space? There are infinite possible images that are there, right, which may not even make any perceptual sense. Amongst all those possibilities, this data set occupies a very tiny amount of space in the ambient manifold is the idea. Okay. Okay. So now why is this an issue for us? The way we constructed Px and P theta, between which we defined the F divergence, they are both supported over RD, correct? They are both supported on RD, correct? Now if you go with the manifold hypothesis, what we are saying is the limited amount of data that we have gotten as training data, which are samples of Px, is supported over a very small manifold in the ambient space. Okay. Now this means that there is this theorem called perfect discriminator theorem, which can be proved, which would say that if there are distributions, okay, whose supports are not perfectly aligned. What is the definition of perfect alignment? Again there is a precise definition of what perfect alignment is. You take two sets upon which distributions are supported. If you can find a bijective map between them, they are called perfect alignment. So if there are two distributions which are supported on sets that are not perfectly aligned, one can theoretically prove that you can always come up with this T function or the discriminator that would give you 100% accuracy. Okay. Fine, let there be a function that gives you 100% accuracy. What is the issue with that? The issue is if you can find a discriminator or a critique function with 100% accuracy, then the GAN training saturates there. Why? Remember how a GAN is trained. Now this discriminator is trying to separate between the distribution, at least in the case of the Jensen-Shannon divergence, it is trying to separate between the samples from Px and P theta. Now if there is a discriminator that gives you 100% accuracy, it completely separates, the generator has no signal to move forward from there, it just gets stuck there, right. So we should not, I mean that is why, remember I told you in the previous class that this min-max optimization problem is not solved in a 1:1 ratio. It is to avoid this. People say that you have to train generator more and discriminator lesser, ratios like 5:1 and so on, whatever, that is a hyperparameter, so that there is no, you do not hit into such a scenario where you get to a perfect discriminator and the training saturates. Now why is this discriminator, I mean saturating? It is because of the manifold hypothesis and the fact that the supports over which the underlying distributions P theta and Px are over, they are not perfectly aligned. If they are not perfectly aligned, you can find a perfect discriminator and therefore the training gets saturated. Okay. What is the solution for this? Okay, so what happens, I mean one can actually show that if you find a perfect discriminator, the divergence metric that we will be computing, no, F divergence, will be independent of the generator parameters theta, that is all it is. I mean what do you mean by saturation? The moment the objective function becomes independent of theta, then it is done. You cannot push the generator parameters any further because it becomes independent of theta, and it can be shown, by the way. The moment you get a discriminator, this can be proved, you can actually take it as a nice homework. What is to be proved is that if you can find a discriminator that gives you 100% accuracy, then the underlying F divergence function that we are looking at will become independent of theta, can be shown. Okay. Once it becomes independent of theta, then the training just stops there because you do not have any signal for the generator function. Okay. Now how do you solve this problem? Okay. In fact, what can be shown is as follows. I do not know if I have it here. I do not. Okay. So there is a degenerative case that one can construct to show this. Okay. What can be shown is, see, suppose you construct two distributions. Let us say in 1 dimensions. Okay, where you have one Dirac delta at some particular place, call it Px. Distribution itself is a Dirac delta at one particular place, call it Px, and there is another Dirac delta at some other place, call it P theta. Compute what the F divergence is, and you can show that things like KL, JSD, etc. will just max out, they will be independent of theta. Now this is, I mean, see, suppose you have, let me write it here. So let us say that we are operating in 1 dimensions and we have two distributions like this. Okay, let us call this P x and this is P theta. We have two distributions like this, and let us say that this is theta axis and this difference is theta. So now these two distributions are not supported on the same point, right? I mean they do not align. What I mean, it is very obvious to see why can there exist a classifier that would classify between these two Dirac deltas. All it has to know is that where are these 2 points supported over, okay, and then you just you just learn to have a threshold between those two and then decide. Now, no matter where these two Dirac deltas are placed, no matter what this theta is, as long as they do not overlap, you can find a perfect discriminator, and you can show that in these kinds of cases most of the f divergence will be either 0 or minus infinity, which will be independent of theta. Now, is not it a better idea to construct a divergence metric that would quantify how far these two Dirac deltas are, instead of just saying whether they overlap or not? Do you understand? So, all the argument so far, I mean, at least in that Wasserstein's metric paper is this, that construct divergence metrics in such a way which would quantify how far or close the manifolds over which the distributions are supported is quantified, rather than just seeing whether they both are well aligned or not. Okay, please take this as an exercise and show that if you have two Dirac deltas, most of the f divergence that are used in practice will max out. That can be shown, that can be algebraically shown. Okay. Okay, so with this is the motivation to why one should move away from, I mean, or rather consider some other divergence metrics than the f divergence. So to answer that question of whether one can find a divergence metric that would facilitate these kinds of properties, people came up with this idea called optimal transport. I mean, which was a classical divergence metric that was there. The question is, how do you translate this metric into a paradigm where you can build a sampler for generative modeling is the question. We will look at that. Okay. So there is this another metric called Wasserstein's metric, which is also called earth mover distance, for the reasons that I am going to tell you. It is based on this idea called optimal transport. So let us look at what it is. So the definition is as follows: given two distributions Px and Px cap, the Wasserstein's distance between them, Px and Px cap, is defined as the solution to this optimization problem. What is the optimization problem that we are considering? Define a sample level distance metric between the samples drawn from Px and Px cap here, x minus x cap, the 2 norm here, the distance between those two vectors. You can in general you can consider P norm. Okay. So let us say that we look at 2 norm. Take an expectation over all possible joint distributions between x and x cap. So consider all possible joint distributions between two random variables, and the Wasserstein's metric is defined as the minimum, not the minimizer, it is the minimum of the expected value of this distance metric over all possible joint distributions over two random variables. When it looks like a complicated definition, it is very intuitive. We will look at why this is an intuitive way of defining it. So lambda here defines a joint distribution between two random variables. Should not. So pi, the search space over which you solve this optimization problem, is all possible joint distributions such that it is not completely open, such that the marginal over one random variable has to be one distribution that we are considering for distance metric. The marginal over the other random variable has to be the other distance metric. The question that we are asking is, suppose you are given two random variables, okay, consider all possible joint distributions and solve an optimization problem over the space of all possible joint distributions between those two random variables. Now it is not unconstrained joint distributions, you have to choose those joint distributions such that the marginals of that joint distribution happen to be the constituent distributions between which you are looking at the divergence. Is it all right? So that is the definition of the Wasserstein's metric. Now many questions here, right? Why would this weird definition constitute a good distance metric, and how do we optimize this to get into a sampler? Those are the questions that we will be answering now. Okay. Any questions on the definition of the Wasserstein's metric? As I said, this can be any distance metric. You can actually take P norm here. If you take P norm, this is called the pth Wasserstein's distance. Whatever I have defined here is the Wasserstein's 2 or 2 Wasserstein's distance. Okay. Okay. Now I'll give a 1D example and motivate why this is a meaningful distance metric to consider, and why do we have this name earth movers distance or optimal transport here. Okay, so let us say that Px and Px cap, the constraint distributions, are two 1D discrete probability mass functions here. We are interested in measuring how far or close these two probability mass functions are in which are supported in one dimensions. They are both discrete distributions, okay, and this is how their distributions look like. Let us say they are both histograms, because we are looking at one dimensions and they are discrete random variables. Okay, now consider this question, is there a way that we can redistribute the mass in Px such that it transforms itself into Px cap? We can do that, right? Meaning we can move some mass or rather we can redistribute some mass in Px such that it get transformed into Px cap. That is possible, meaning for instance here there is a lot of mass here at x1, you just take some mass from x1 and put it to x3 and do that redistribution, and if you do that then you will get to Px cap from Px. Does it make sense? Okay. So, the mass in Px can be redistributed such that Px transforms or rather gets converted into Px cap. Now, here is the question that I ask you, how many ways can one redistribute the mass in Px such that it gets Px cap? Is it a fixed scheme or can it be done in multiple ways? You got the question, right? I want to redistribute the mass in Px. Now, is there a one fixed way of doing it, or can you think of multiple ways of doing it? There are multiple ways of doing it, correct? Now, here is my claim, every redistribution scheme that would transform one distribution into the other can actually be represented as a joint distribution between Px and Px cap. Every redistribution scheme that would convert Px into Px cap can be represented as a table. Okay, so first of all, before calling it a joint distribution, do you agree that it can be represented as a table? Why? What am I saying is, take all the values that Px would take and take all the values that Px cap would take. Okay, what are you actually doing? Take some mass from Px and put it at different other places so that it gets converted into Px cap. Okay, and you can do it in multiple ways multiple ways at every support point of Px, isn't it? And it has to be done in such a way that the sum of all of it has to sum to 1. Why? Because you have 100% mass to be redistributed and all of them are bounded between 0 and 1, because it is a percentage of mass that you are redistributing. Also, when you redistribute, it has to be redistributed such that if you take one row or one column, it had to look like the other distribution, correct? Isn't it a joint distribution? All I am saying is, you know what, joint distribution, if you take a joint distribution and sum over one particular random variable, that procedure is called something. Do you know the name? It is called marginalization. Why? Because you are actually summing over the margin of this table. It is called marginalization literally because you are summing over the margin of this table to get the other distribution. So, every marginalization scheme should be looked into as a redistribution of masses in one of the distributions so that it gets converted into other distribution. When it is very easy to see it in the discrete case, that is why I have showed it as a discrete case, you can have a similar argument in the continuous case. So, every redistribution scheme, which is also called the transport scheme, that is why the name optimal transport, we have not talked about optimality yet, we are only talking about the transport scheme. Every redistribution scheme that would redistribute the mass which is in the support of one distribution so that it becomes the other distribution is called a transport scheme, and it can be represented as a joint distribution. Every joint distribution between two random variables is actually giving you a redistribution scheme so that you make one distribution into the other and vice versa. You can have infinite such tables here because you can have infinite distributions such that the marginals are the constant distributions. Okay. Okay, so now every redistribution scheme is a joint distribution and is called the transport plan. Now the question is, we are converting one distribution into the other and that is quantified using a joint distribution. Now what am I interested in is, what is the effort associated in moving that mass so that it gets converted into one distribution. So given that I have so many transport plans, see where am I going, actually I need to define an optimality between the possible transport plans. To do that I will have to define a way to quantify what is the effort that is needed to make one distribution to the other. Okay. So now we have to quantify the effort involved in one particular transport plan. So when I say transport plan I am talking about a redistribution scheme which is also a joint distribution, correct. Okay. Now let us define that. There are again so many ways to do it, people have done it in this one way. Suppose some mass is moved from a place x to x cap, where x and x cap are two dummy points to represent 2 points on the support of distribution that we are looking at. Let us say that we move some mass from x to x cap. Now the distance of the movement can be quantified as the norm of the difference vector x minus x cap, that is the distance. What is the mass that was actually moved, that can be quantified using the likelihood of those 2 points under the joint distribution that we are considering. In fact, it is very easy to see. If you take this table which is a joint distribution, every entry here is actually telling you what is the amount of mass that is to be moved from this point to this point so that it gets converted, that is what it would say. Okay. So that is the amount of mass that was moved and this is the distance with which it was moved. Now if you multiply those two, your high school physics tells you that it will tell you the work done in moving the mass from x to x cap. So that is why the name earth mover distance, you are actually moving earth which is dirt from one point to the other so that the distributions get converted. Okay. So this will tell you what is the effort that is needed to move one mass to the other, a mass of pi x comma x cap from point x to x cap. Okay. Now we need average work, again high school physics, right. I mean if you want to quantify the average work, you just integrate all of that over all possible masses. I mean I just made a jump now from discrete distribution to continuous distributions. Even either you take a sum over all possible values or you take an integral. The moment we have integrals and distribution functions, we know what they are expectations. So the expectation of some kind of a norm of the difference between two vectors upon which the distributions are supported, the expectation is taken over the joint distribution, will give you the average amount of effort or work that is needed to convert one distribution to the other using this particular transport plan which is a joint distribution. Make sense? Now the next question is, given that multiple transport plans which are joint distributions that exist between two random variables, which of them correspond to the least amount of work done? How do you quantify this? Solve an define it as an optimization problem, okay, over the average amount of work done. You will have to ensure that the transport plans are considered in such a way that operating the transport plan always leads you to one of the constituent distributions. That is the constraint with which we solve the optimization problem. Consider all joint distributions such that the marginals become the underlying constituent distributions, okay, and you solve an optimization problem saying that amongst all possible transport plans, which is the one that corresponds to the least amount of effort. Now that is what is defined as the Wasserstein's metric. Okay. Now the transport plan that leads to the least amount of effort is what you get by solving this optimization problem. Now here is the intuitive idea, right. The closer the distributions are, the lesser the least amount of effort that is needed to make one distribution to the other. So we do not care about the higher efforts that are needed. Tell me what is the least amount of work that I have to do to convert one distribution to the other, okay. Now amongst all possible transport plans, if I can find out what is the least the transport plant with the least amount of effort, that will give me how far or close the constituent distributions are, and that is why Wasserstein's metric is a good uh, divergence metric between pair of distributions. In fact, we will go back to the example, right. You can take it as a homework and solve it. You can show that for this degenerative case, the Wasserstein's 2 metric, okay, will be proportional to theta. It can be shown that it is actually the magnitude of theta. The closer they are, the lesser the Wasserstein's 2 metric is. Unlike the other distance matrices, right, F divergences that which would max out. Make sense? Yeah. So here is the definition of Wasserstein's metric. Wasserstein's, yeah, P Wasserstein's metric in general is given as the solution to this optimization problem, which is solving minimum amongst all possible joint distributions such that the marginals are the constituent distributions. The minimization is over the norm of the difference between all possible pair of values on the support of the constituent distributions. This is the definition of Pth Wasserstein's metric. Okay. Any questions? Yeah, so here is a fact, right. Wasserstein's metric does not saturate unlike F divergence when the supports of Px and P theta do not align. I talked about the degenerative case where you have Dirac deltas and the distributions are completely supported at two different points, but even in higher dimensions what can be shown is this alignment. Okay, just define what alignment is. Even if the supports of these two distributions are not perfectly aligned, the Wasserstein's metric would not saturate. Now let us get back to what we are interested in. We are interested in constructing samplers. Okay. Now the paradigm, the framework remains exactly the same. We start with an arbitrary random variable and we have a function, and then we have the outcome of it, and we want to tweak the parameters of that function such that some distance metric is minimized. Now instead of using F divergence which we were using so far, now we need Wasserstein's metric to be optimized. All we did was change the distance metric. Okay. Now, yeah, now the next question is how do you minimize the Wasserstein's metric? So we have the same problem. We have expectations, do not know the underlying distributions. How do we have to minimize? Thankfully, there is this nice idea called Kantrowicz-Rubinstein's duality, which would say that you can express the Wasserstein's metric using a maximization problem, which is the dual of the original minimization problem that we had, and this maximization problem has a very similar form to the F divergence minimizer, the lower bound that we constructed on F divergence, which is the difference between two expectations. I will not go to the proof of this. Okay. All this is saying is that Wasserstein's metric can be expressed as a maximization problem over a class of functions. I will define what these functions are. So first you have an expectation over some function Tw of x, and the expectation is over one distribution, and the second expectation is over the other distribution. A very similar way, but it is not exactly the same, right, because the F divergence had an F star here and so on. It does not have it that way, but it is simply the difference between two expectations of functions that we can estimate, and the expectations are over the distribution of interest. That is how this will turn out to be. The rough idea of this is, see, every optimization problem will have a dual, you see, you know that, right. A primal problem will have a dual problem. It is the same duality that will lead to this particular problem. Okay, if you are interested, you can go and read the original paper for the proof of this. How do you get this? But you take it as a fact that this can be represented as a maximization problem now. Now this T function there, what was the T function? The T function there was the function that we used to define the bound when we were moving the supremum outside of the integral, right. What is the T function here? T function here are all functions, any function such that they are one Lipschitz. What is the definition of Lipschitz continuity? Specifically, one Lipschitz continuity is that their derivatives are bounded at all points. Or in other words, I am saying if you take 2 points x1 and x2 and evaluate those 2 points under this function and divide with the norm of the difference, that should be bounded. One Lipschitz is this. So now what we are saying is that solve an optimization problem, okay, over all possible one Lipschitz functions to get the Wasserstein's metric. Okay. Now the final optimization problem that we solve here to get our generative sampler again boils down to be this, which is that solve the inner maximization problem to get the Wasserstein's metric evaluated, and you have an outer optimization problem with respect to sampler, so that we make sure that p theta is close to px. Now this is how it becomes a GAN now. So this is adversarial again. Why? Because this is also solving a min max optimization problem just like f divergence minimizer. Above objective is similar to that of GANs, therefore this method of minimizing Wasserstein's metric, people call it WGAN, Wasserstein's GAN, for obvious reasons. It see how these ideas converge, right? I mean the optimal transport and Wasserstein's metric do not have any bearing as such with the f divergence minimizer. In fact, even historically, as I said, the very first paper that talks of GAN, okay, I mean, by the way, I forgot to mention this, but I strongly recommend that all of you go back and study the original papers that I am discussing here. One is the original GAN paper, the other is the FGAN paper. It is called F divergence, variational F divergence minimizer. I mean, I should not be saying this, but still a hint is that your exams and the other things will depend upon some of the ideas that are discussed in that paper. So strongly urge that all of you go and read those original papers. There are so many things that cannot be covered in class that are there, so please go and read that. As I said, yeah, chronologically what happened was that first the GAN paper came, and the treatment there was that you are looking at a classifier guided sampling, the one that we discussed the last class. Couple of years after that came the F divergence paper that would say that the GAN that was discussed or proposed was a special case of these large class of methods called F divergence minimizers, and in between, people were struggling to train these GANs because of the saturation problem. Okay, and then people came up with this optimal transport. They said, okay, why is this happening? Why is this problem of saturation coming up? Okay, and then they realized that it is because of the fact that because of the manifold hypothesis and the supports are not aligned, therefore it is coming. And they said, okay, we'll look at another divergence metric, and optimal transport was proposed, or rather used, because optimal transport is an idea that dates back to several decades, okay, 1950s and 60s. And then they found out that even if you have a Wasserstein's metric, nothing much changes. Okay, only there is a slight change in the objective function. And the other thing is that the so called critique network, and how do people realize this TW is through another neural network. Just like we had a critique network, the Wasserstein's GAN also should have this function that would define the Wasserstein's metric, that is represented as another neural network. The only constraint that is there in Wasserstein's GAN is that you will have to ensure that your critique network is one Lipschitz. Now the question is, how do you ensure that the neural networks, yeah, this is what it is, right. So you have another network which is the critique network, which would give you that TW function that would define the Wasserstein's metric. The only thing is it had to be made one Lipschitz. How do you make a neural network one Lipschitz, have bounded derivatives? Does anyone know? A neural network is a composite function of sigmoids, isn't it? So if you have multiple compositions of sigmoids, all of them have well defined derivatives. How do you make sure that they have bounded derivatives? One thing to do is that you normalize the weights of the neural network after every iteration such that the two norm of the weights is equal to 1 at all layers. You do it with every single individual weight. This will ensure that the neural networks that you are training are one Lipschitz. That's all. So you are for doing nothing, right? Only by normalizing the weights during training, you get so much of advantage. The conclusion is training a WGAN is more stable compared to that of a naive GAN, and that's why when people train GANs today, it's always the WGAN that is trained, in the sense that the weights are normalized. You don't have to do anything much. The same GAN is being trained, but if you just do weight normalization, then you get so much of benefit that it is stabler compared to the naive GAN training. That's it for today. We'll see you in the next class. Thank you.